Okay, so a quick reminder of how the solubility chart works. Okay, what we do is we look for our non-metal, okay, which is going to be on that top row, and then we see if the metal it's with is listed either in the first row, meaning it would be soluble, or the second row, meaning it would be not soluble. All right, so for our first one here, we've got calcium sulfate. Right, so sulfate is right here. Okay, and we can see that it says it's soluble with most things, but calcium is listed first in the second row. Okay, so calcium sulfate would be not soluble. Right. Potassium hydroxide, so we look up hydroxide, it's at the very end right here. Okay, it says it's soluble with anything in group 1. Okay, well, group 1 is the first column on the periodic table, and that is where you can find potassium, so that stuff is soluble. Okay, is this ringing a bell? Okay, lead 2 chloride. All right, so we need we need to find chlorine first. Okay, chlorine is right here, and it says that it is soluble with most things, but not with copper, silver, mercury, or lead with the 2+ charge. So this stuff is not soluble. Okay, for tin 4 fluoride. Okay, so fluorine is right here. It has its own column. Okay, it says it's soluble with most things, but I don't see tin listed here. Okay, so that must mean that tin 4 fluoride is in fact a soluble compound, as it's not listed there in the second row, so it must be part of most. Okay, so this stuff is soluble. Okay, and then we have copper 2 sulfate. Okay, so we go back to sulfate, which is right here, soluble with most things. Okay, so I got to check in this row here. I don't see copper listed there, so that must be part of most, and that one would be soluble. Okay, for number 6, we've got potassium bromine, okay, or bromide, sorry. So bromine is in the same column as chlorine and iodine. Says it's soluble with most things, and I don't see, no, copper, sorry, potassium is not listed here. Okay, so that one would be soluble. And then we have silver fluoride. Okay, so fluorine again is this column right here, right? Says it's soluble with most things. I don't see silver listed here in the bottom row, so that stuff would be soluble as well. And then we have beryllium nitrate. As a general rule, nitrates are all soluble. Okay, but we can double check. Says soluble with most, except for these complex things that obviously are not beryllium, so that would be soluble as well. Okay. Questions on how that works? All right, so what you went over with Mr. Van Erve on the Friday before the break, okay, was the signs of a chemical change. Okay, so quick review here. The signs of a chemical change are that there could be a color change, there could be a new odor, there could be a state change, a precipitate could be formed. Okay, there could be an energy change, an increase or a decrease in temperature. Okay, the big thing for a chemical change is this: your final products are chemically different than your starting reactants. Now let's quickly review what those terms mean here. Okay, so if I have, let's say, this reaction here. Okay, potassium iodide is reacting with lead 2 nitrate. Okay, that's going to form potassium nitrate and lead 2 iodide. Okay, and we would need a 2 here and a 2 there in order to make it work. Okay, so in this reaction that I've written out, these are my reactants, because they are the things that are going to react with each other. Okay, over here on this side are my products, because it is what is produced by the reaction. So when I say reactants and products, that's what I mean. They're the two sides of a chemical reaction. Okay, so my products are chemically different from my reactants. They're still made up of the same elements. Okay, we can't go against what Dalton said in his atomic theory. Okay, in Dalton's atomic theory, he said that in a chemical reaction, atoms can be separated, they can be joined, they can be rearranged. This is an example of a reaction where they are rearranged. I still have the same elements, but I don't have the same materials. Okay, I know that might seem contradictory, but I'm going somewhere with this. Okay, on this side I have potassium iodide, which is a clear solution. Okay, on this side I have lead 2 nitrate, okay, which is also a clear, somewhat cloudy solution. Okay, when I mix these two things, a reaction occurs that produces potassium nitrate, which is a clear solution, and lead 2 iodide, which is a bright yellow solid. Okay, a precipitate gets formed in this reaction. Okay, so when I have this reaction happen, what I see at the end are two different compounds, different materials, made of the same elements that I started with. Okay, but I definitely have different materials because I see materials on this side that have different properties than what was on this side. Okay, both of these compounds were soluble. Okay, they were both clear solutions. When I was done, I had one clear solution, but I had another thing that wasn't soluble anymore. Okay, their physical properties have changed because I've I've formed new materials, new compounds as a result of the reactions. Everyone kind of follow what I mean there? Okay, we still have the same elements, but because we put them with new partners, we have new compounds that have different properties than what we started with, and that's why we see the signs of a chemical reaction that we see. Color changes, precipitates being formed, okay? Changes in state, changes in energy, all of that kind of stuff. Okay? Everybody all right with that idea? Okay, so it's pretty important to understand what happens in a chemical reaction. Okay? And you can always go back to Dalton's atomic theory, point number 3, okay? Point number 4, in order to get that. All right, so what we're going to go over now are the different reaction types, okay, and learning how to write a chemical equation, okay? That's what I did right here. I wrote a chemical equation, which means I write out the formulas for each of the compounds that are involved, okay? If they're ionic, I make sure they're dropped and swapped. And then what I do is I make sure that I obey the most important law there is, the law of conservation of mass, or the law of conservation of matter. Either way is fine. They mean the same thing. Okay? What that means is that I have the same amount of matter at the beginning as I have at the end. Okay? So if I'm looking at my reaction here, okay, on this side of the reaction, on the reactant side, okay, I've got 2 potassium iodide molecules. Okay? I've got 1 lead 2 nitrate molecule, which contains 1 lead atom and 2 nitrogen, or 2 nitrates, we'll say. Okay, everybody follow me there? How am I counting? Okay, so I've got 2 molecules of potassium iodide, 1 molecule of this. On this side, I have 2 molecules of potassium nitrate, but there's a 2 here, right? So there's 2. That means there's still 2 nitrates, and I had 2 nitrates over here. Okay, there's still 2 potassium. I had 2 potassium over here. Okay, I've got 1 lead, and 2 iodine. 2 iodine. So my equation is what we call balanced, meaning I've obeyed the law of conservation of mass. I have not created matter, and I have not destroyed matter. Right? I've rearranged it, but I've conserved it all. Okay? And it's important that we do that because you cannot create or destroy matter. Okay. So, we talked about this already. Okay, so first type of chemical reaction, and we're going along with what Dalton said happens in a chemical reaction. Atoms can be joined. Okay, in a synthesis reaction, that's exactly what happens. I am joining 2 elements together to form a single compound. Okay, I am synthesizing a new compound from its base parts. All right, so these 2 things would be examples of synthesis reactions. Okay, I react solid magnesium with oxygen, which is really easy. You just leave the magnesium out in the air, okay, and it will react with oxygen in the air and it'll turn kind of black. Okay, that'll form magnesium oxide, which is the equivalent of rust. Okay, it's like when if you leave iron out, it'll rust. Okay, if you leave magnesium out, it also oxidizes, reacts with oxygen, okay, and corrodes. Okay, so that's essentially what we have here. Magnesium oxide is a solid. Okay, oxygen is obviously a gas. Magnesium is a metal, so it's a solid. You're never going to have to worry about writing the states of matter in Science 10. Okay, you will in Chem 20, but you don't have to worry about it for here. Okay, our second example, okay, I've got 2 potassium atoms, okay, reacting with 1 molecule of bromine, okay. Why is this a molecule and this 2 separate atoms? The answer is the way they're written. Okay? If I have a big 2 in front, it means there's 2 of these that are separate. If I have a little 2 as a subscript behind, it means these 2 things are joined. Okay? They're a molecule then. Okay? They're joined together chemically. Right? So bromine is one of a group of special elements, okay, called the molecular elements. Okay? And they simply bond with themselves. Oxygen is also a member of that group. Okay? In fact, if you take out your periodic table, you can see which ones are part of that group because they're the ones that are color-coded on your periodic table. Okay? They're also listed up top here as well. They call polyatomic elements on your periodic table. Okay? There's a list of them there, and they're color-coded on your periodic table. So anything that's in yellow, okay, comes as a pair. Right? Hydrogen should also be yellow. Okay? It's not for some reason, but it should be. Okay? And then you've got phosphorus, which is purple. Okay? It bonds with itself 4 times. And you've got sulfur, which is orange. Okay? And it bonds with itself 8 times. Okay? So you've got those things that come as a molecule. All right, so these 2 elements still react with each other to form a single compound. And that's what always happens in a synthesis reaction. You have 2 reactants, and they react to form a single product. Okay? Now, I've said that about 4 times, and the reason I've said that about 4 times now is it's important to be able to identify a reaction type. Okay? When I look at a reaction, I've got to be able to go, oh, that's a synthesis reaction, that's a combustion reaction, that's this kind of reaction. Okay? We need to be able to do that because as we move along, we're going to have to predict the products of a chemical reaction. So all you would be given is that part, the first part, and you would have to predict from there what the products would be. Right now that probably sounds intimidating, but trust me, it's really not that hard. You know what has to go together, right? You know these are the 2 things that are reacting. There's only a certain number of things that can happen. Okay? All right, everybody okay with synthesis? All right, the other thing that Dalton said could happen is atoms could be separated. That's a decomposition reaction. Okay? In a decomposition reaction, we only have 1 reactant. And that reactant is going to break down into its parts. Okay? It's usually 2 elements, but it can sometimes be an element and a compound. Okay? It depends on the reaction, but for our purposes, it's going to be a single compound breaking down into its 2 elements. Right? So the examples we have here are water, okay, breaking down into hydrogen gas and oxygen gas. Okay? Again, the states of matter aren't important for us. Okay? Did I conserve everything? Do I have the same number of everything on both sides there? Okay. How many hydrogens do I have here? Okay. 2 times 2 is 4, right? This is saying I have 2 molecules of water. Each molecule of water has 2 hydrogens in it. So whatever this number is, you multiply everything in the compound by it. So there's 4 hydrogens here. How many are there here? 4. Okay. And how many oxygens are here? Every water molecule has 1 oxygen, but I have 2 molecules of water, so I have how many oxygens? 2. Do I have 2 over here? Yep. O2, right? That means that they're bonded together, so I've got 2 oxygens on both sides. The reaction is balanced. I've obeyed the law of conservation of mass. All right. The second reaction here, we've got nitrogen triiodide, 2 molecules of it, breaking down into nitrogen and iodine. Right? Are you okay with that? Is this one balanced? Okay. How many nitrogens do I have on this side? Okay. There's 2 on this side. Remember, this 2 means multiply everything in this compound by 2. So there's 2 nitrogens, right? Because there's no number beside it. So 2 times 1 is 2. Okay. Are there 2 nitrogens over here? Okay. How many iodines are there here? 6. 2 times 3 is 6. Over here, 3 times 2 is 6. We're still balanced. All right, so simple decomposition is just that, simple. It's just a compound breaking down into its elements. Okay, and sorry, this was what we just went over a minute ago. That's your periodic table. Okay, so all the polyatomic ones are listed up top here. Okay, I did color code them just so as kind of a quick reference. So if you're just looking at your periodic table, you're, oh right, that one's, because I find people miss this. It's really small up top. Okay, all right. Combustion reactions. So combustion means burning. Okay, if something's going to burn, what gas is required? Oxygen. Okay, you cannot have a fire without oxygen. Okay, you probably did that experiment in grade 1, you know, where you had the candle and you put the jar over top of it and eventually it went out, okay, because it burned up all the oxygen that was inside the jar. Okay, so what we have here, okay, is what we call hydrocarbon combustion, and that's the type of combustion we're going to deal with. Okay, a hydrocarbon is any compound, that is molecular, containing carbon and hydrogen, hence the name hydrocarbon. Okay, this is a very common hydrocarbon. It's propane. Okay, so it's the stuff you use in a barbecue or something like that. Right? So propane is reacting with oxygen gas. Okay, whenever something burns, if it burns purely and completely, the only products of that combustion are carbon dioxide and water. Okay. Sometimes that water can be liquid, sometimes it's going to be a vapor. It depends on how well the combustion reaction is occurring and what temperatures it's occurring at. Okay? Most of the time the water is going to be a vapor, okay? Which is why you can see obviously stuff coming out of like exhaust pipes and stuff like that when you're burning gasoline. Okay? Most of the smoke is actually water vapor. Okay? There's still obviously carbon dioxide in there, okay? But most of that is water vapor. But on a really cold day, if you've ever looked, you can usually see liquid water dripping out of the exhaust pipe of a car. Okay? That's because the ambient air temperature is cold enough that the water vapor is actually condensing inside the exhaust system, and the force of the air is actually just blowing it out the back. All right, so in any combustion reaction, you start out with a hydrocarbon, you have oxygen reacting with it, and that's going to produce carbon dioxide and water. Always. This is just one you have to remember. Okay? A combustion reaction always produces these two things. Okay? And for us, we're dealing with pure, simple combustion. Okay? In real combustion, other things are usually produced as well, but it becomes a lot more complex for us to keep track of them, so we don't in Science 10. Okay? Obviously, in real combustion, other gases like carbon monoxide, sulfur dioxides, and things like that are produced because they're additives to the fuel. Okay? All right. Now, for combustion reactions, we have to balance them a little bit differently. There's a couple of special rules for balancing a combustion reaction. So I'm just going to kind of go over those here. Okay, I'm going to rewrite that reaction. C3H8 plus oxygen gas gives us carbon dioxide and water. Okay. Because combustion reactions are a little different, okay, we balance them different than all the other reactions. Okay, and I haven't even taught you how to balance the other reactions yet, but I want to go over the special rules for these. You're just going to need to write them down. Okay? There's two rules for balancing a combustion reaction, and they are: balance in alphabetical order. Carbon, then hydrogen, then oxygen. Okay, always in that order. Okay, the second rule we call the rule of two. Okay, and I don't mean the Star Wars Sith rule of two. There's always a master and apprentice. It's a different rule. Okay, even though that's a really cool rule. Star Wars used to be cool. Anyway, okay. So we've got the rule of two, which means that if you have an even number of carbons, start the reaction with a 2. I'll show you what I mean by that in a minute. Okay. So for this reaction, sorry, no.
Oh, so when we had the feature on Friday,
Yeah.
is the one that you had before an even number of carbons you have balanced with the two?
Yes, I wrote it like Yoda would say it.
Yeah.
Yeah, same rule. Yeah. I wasn't sure. I did the Yoda voice too, didn't I? In the recording?
Yeah.
Yeah. I'm feeling up to that today. All right. Okay, so for our first reaction here, we don't need the rule of two. Okay, we just don't because we have an odd number of carbons. Okay, so we don't need to start with a 2. All right, so what I'm going to do is just follow rule number 1 and balance in alphabetical order. How many carbons do I have here? Okay, let me make it simpler. What number is this? 3. Okay, that means I have 3 carbons. All right, so I'm going to go over here. Over here, I only have 1 carbon. Okay, that's not good. I need to have 3. So what I do is I put a big 3 in front of carbon dioxide. Now I have 3 carbons. I also have 6 oxygens there, but I'll deal with that later. For right now, my carbons are now balanced. There's 3 on each side. Everybody follow what I did there? Okay, why didn't I just do this? Then I changed the compound. It's no longer carbon dioxide, it's tricarbon dioxide. I have no idea, that probably doesn't even exist. Okay, I can't put in little numbers. Okay, I can change how much of something I have, I can't change what I have. All right, that's the rule of balancing. You can add more, you can take it away, but you can't change it fundamentally. All right, so I've got 3 carbon dioxides. All right, next thing I gotta balance, hydrogen. So I go back over here. How many hydrogens do I have? 8. Okay, so I got to go over here. Over here I only have 2. Well, what times 2 will give me 8? 4. Perfect. So I put a 4 in front of that. Now I've got 8 hydrogens on each side. Okay, the math is really easy. Okay, now I've got to balance my oxygens. I'm supposed to do that last. Over here I have 2. How many do I have over here? I've got 3 times 2 is 6. Plus 4 more is 10. Okay, this is why we do oxygen last. Okay, so I've got 4 oxygens here with the water. I've got 3 times 2 is 6 oxygens here. 6 plus 4 is 10. What times 2 will give me 10? 5. Done. Reaction is balanced. Okay, now everything is equal on both sides. Okay, and really balancing other reactions, the process is similar. We just don't have to do it in alphabetical order. You have to do combustion reactions in alphabetical order just because they work out easiest that way. Okay? All right, so that's that reaction. We didn't have to use rule number 2. For this one, we will. Okay, so it's still a combustion reaction because I have a hydrocarbon reacting with oxygen gas, so it's burning. Okay, this is butane. It's in lighters. Okay, I still want to balance in alphabetical order, but now I have to use the rule of 2 because 4 is an even number. So it says if you have an even number of carbons, start the reaction with a 2. So what that means is put a 2 right at the beginning of the reaction. Everything is going to be multiplied by 2. Right? Now, the reason we're going to do this is as follows. If I don't put the 2 there and I just start balancing, I've got 4 carbons, so I put a 4 here. I've got 10 hydrogens, so I go over here and I put a 5 here. Okay? Now is where I'm going to run into problems. 4 times 2 is 8, plus 5 is 13. What times 2 gives me 13? 6.5. Can I have 6.5 molecules? No. Okay? That's why we have to put a 2 in front. The 2 will eliminate this decimal that we're going to get if we don't do that. All right, so I'm going to put a 2 in front of this. That'll eliminate that problem. So 2 times 4 is 8 carbons. Everybody with me there? Okay, so I'm going to put an 8 here. Now I'm going to, alphabetical order, I got to do the hydrogens next. 2 times 10 is 20. So I need 20 over here, so what goes in front of the water? 10. So 10 times 2 is 20. Okay, now I can look at my oxygens. I've got 10 oxygens here in the water. and another 16 oxygens here in the carbon dioxide for a total of 26. What times 2 gives you 26? 13. And now the reaction's balanced. Okay? So that's why we start with a 2. It eliminates that 0.5. You never put a decimal in a reaction. Okay, questions on that? Does anyone still need this? Okay, is that as far as you got with Mr. Banner? The combustion?
Single replacement.
So, oh, you got a single replacement. Okay, so single replacement reactions, okay, involve the rearranging, okay, same as combustion. Combustion's a rearrangement as well, okay. But if we're talking about Dalton's atomic theory, okay, these are reactions where atoms are being rearranged, okay, they're being given new partners. All right, so in this particular reaction, I have copper by itself, so a metal acting as an element, okay, reacting with an ionic compound, silver nitrate. Okay? Replacement reactions always involve ionic compounds. They never involve molecular compounds. Okay? They can't because they require a switching. Okay? A metal or a non-metal has to switch places with the thing it's like in the reaction, and that can't happen if you've got molecular compounds. All right? So what we have with this here is we have a metal reacting with an ionic compound. The metal will replace the metal in the ionic compound. Okay? If this was a non-metal, then it would replace the non-metal in the ionic compound. Okay? So whatever is alone in a single replacement reaction, it's going to replace the part of the ionic compound that it is the same as. Okay? So in this case, copper is going to replace silver because silver is a metal and copper is a metal. Okay? Everybody all right with that? Okay. So what ends up happening then is silver ends up alone and copper ends up in a compound with nitrate. Okay? So the diagram here is showing there's this guy and he's by himself, and there's this couple that's dancing, and he decides that she needs to be with him, so he gets rid of him and takes off with her. Now you've got a different pair, okay, or a different couple together, and you've got someone else now who's alone. A different person is now alone. Okay, everybody all right with that? Okay, now obviously the partners dancing thing kind of breaks down a little bit if you're looking at how relationships work. So it's just a loose analogy, okay. But in chemistry, you couldn't have the metal get rid of the non-metal, and then the two metals would be together. Okay? Chemistry is very old-fashioned, and it wouldn't like that. Okay? I'm not saying there's anything wrong with that in real life, okay? But chemistry is old-fashioned. I have to make an ionic compound, and I can't do that with two metals together. Okay? Everybody kind of follow me here? Okay? There has to be a switching of the things that are alike. Okay? So, in terms of balancing here, okay, how many copper do I have on this side? One. How many copper over here? One. Okay. How many silver do I have here? Two, right? Because there's a big 2 in front of this. So there's 2 silver. Over here, also 2 silver. All right, here's the tricky part. How many nitrates do I have? That's usually the gut reaction, 6.
We only have 2.
Right, we have 2. Okay? Remember, nitrate is NO3. It's not breaking up, it's staying together. Okay, so there's 2 nitrates. Over here, there's how many nitrates? 2. That's why we enclose them in brackets if we're going to have that 2 outside. We learned that when we were learning how to write formulas and names. Okay? Everybody all right with that? Okay, so all we see in a single replacement reaction is the thing that's alone replaces the part of the compound that it's like. So let's look at a slightly different one here. Let's look at okay, so I've got iodine, which is metal or non-metal? It's a, which side of the?
Non-metal.
It's a non-metal. Okay, it's on the right of the staircase. Okay, it's reacting with this ionic compound, potassium chloride. So what part of potassium chloride is iodine like? Potassium or chloride? It's like chloride, right? It's a non-metal. So those are the two that are going to switch places. So that means chlorine's going to end up alone, and iodine is going to end up with potassium. Okay, how did I know to put a 2 beside chlorine when I wrote that? The answer is I took a quick look at my periodic table and saw that chlorine was yellow on my periodic table. That means when it's by itself, it's never alone. It's always got a partner. Okay? It always comes as a 2 when it's by itself. Doesn't always come as a 2 in a compound. We can see that here. Okay? But when it's by itself, it always comes as a 2. Iodine, same thing. Right? So I knew to put a 2 beside it. I know iodine goes with potassium this way because it's a +1. This is a -1. So I've dropped and swapped that compound fine. Okay. So now that I've done that, now I need to balance the reaction. So what should I start with if I'm going to balance this? Because I don't have to do this in alphabetical order. Okay. The general rule I always follow, the biggest number first. Okay. Now, there's 2 things in here that are 2s, so I can pick either one. Okay. I'm going to start with iodine. There's 2 iodine on this side. How many are there over here? Just 1. I can't put a little 2 here, so what do I have to do? Put a big 2. All right, so I've put a big 2 there now. Now how many potassium do I have? 2. So now I got to go back over here, and I got to make sure I have 2. I can't put in a little one, so I've got to put a big one. Okay, when I do that, how many chlorine do I now have? 2. How many do I have over there? 2. Always a good sign if when you're just about done, the last thing you check has the right number on it. If that doesn't happen, then you got to go back and check it again. All right. So, single replacement reactions. Element reacts with ionic compound and replaces what it's like. All right. Double replacement reactions are similar to that, but they involve 2 ionic compounds reacting with each other. Okay, so now you have 2 compounds instead of an element in a compound. Okay? Double replacement reactions look like they're the toughest, but they are actually the easiest. All you have to do is switch the metals. That's all that's going to happen in a double replacement reaction. Okay? This is essentially, instead of having the one guy alone and the 2 and the couple, it's 2 couples. And all they're going to do is switch partners. Okay? So we've got calcium and chlorine together, sodium and carbonate together. So all that's going to happen is calcium and sodium are going to switch places. Okay? And on the other side, we have 2 different ionic compounds. So again, it's like what Dalton said, they are being rearranged. Okay? The atoms are being rearranged. All right, so is this reaction balanced? What I usually do if I'm checking if it's balanced, I just pick something. Okay, there's 1 calcium over here. And there's 1 calcium over here. So far, so good. How many carbonates are there? 1. Okay, there's 1 carbonate, right? This is carbonate, CO3. And there's 1 over here. Okay, there's 2 chlorines over here. And there are 2 chlorines over here. There are 2 sodiums here. And 2 sodiums here, so yes, that reaction is balanced. Okay. All right. Everybody okay with those ones? All right, so we've talked about the balancing. This is just kind of the written part of balancing. We're just going to kind of skip over that because we've done it a couple times already. Okay, here's what I want you guys to try. Okay. I want you to do 3 things with these 2 reactions. Identify what type it is. Single replacement, combustion, whatever. Okay, we only went over 5, so identify the type. Okay, balance it. So put in the big numbers if they're needed. And write it out in words. That means write the names for all the parts. Okay, so let's do the first one together just so you kind of see what I mean. All right, so if I'm writing this first one out in words, okay, N2 is just nitrogen. Okay, it's not dinitrogen. This is how nitrogen appears as an element. Okay, it's one of our special ones. It's yellow on your periodic table. Okay, it's reacting with hydrogen, which is another one of the special ones. I don't have to put di in front of it. It's an element. Okay, and that's going to form this compound, which is molecular. So I have to follow my molecular naming rules. This will be nitrogen trihydride. Okay, what kind of reaction is that? It's a synthesis reaction. I have two elements combining to form a single compound, right? So that is a synthesis reaction. And now I need to balance this. Okay, this one's a little trickier. My biggest number is 3. Okay, so I'm going to start with my biggest number. Now, I've got 3 hydrogens over here, and I've got 2 over here. How am I going to make that work? Okay, so I put a 2 here. Okay, I like how that starts. Okay, when I put a 2 here, that gives me how many hydrogens? 6. Okay, so what needs to go in front of this then? A 3, right? Okay, essentially you have to find the lowest common multiple, okay, and make sure that they both add up to it. Okay, all right, when I do that, that gives me 2 nitrogens, which also happens to make my nitrogens work, so not good. Okay, you try these 2. Now, there are special rules for this one. Okay, let's look at the second one here. So I've got nitrogen, okay, if we're just going to write this one out in words, okay, so I've got nitrogen, okay, plus calcium chloride, okay, ionic compound, so I just follow the ionic naming rules. Okay, this is, guys, why naming is so important, right? We can't write a reaction properly if we can't write the names of the compounds in it, okay? And this is going to be an ionic compound, calcium nitride. Okay, and chlorine. Okay, so that reaction is written out in words. What kind of reaction is it? It's a single replacement reaction. Okay, and we know that because we have an element reacting with an ionic compound. So it's also important to be able to identify whether something's ionic or molecular in order to do this. Okay, so this is a single replacement reaction. Okay, I need to balance everything. My general rule is start with the biggest number. That would be calcium. Right? So I've got 3 calcium on this side, so what do I need to put right here? Okay, well, if I want it to balance, okay, I need what number right here? 3, yeah. Okay, I've got 3 calcium here, so I need 3 calcium on this side, right? This essentially means there's 1 calcium, 3 times 1 is 3. Okay, as soon as I do that, that gives me how many chlorines? 6. Okay, so I've got to go over here and make sure that I have 6 chlorines. So what goes in front of this? 3, because 3 times 2 will give me 6. Okay, and this is kind of what you do. You hop back and forth from products to reactants and reactants to products. Okay, I've got calcium balanced, I've got chlorine balanced. Now I've got 2 nitrogens on this side, and, always a good sign, 2 nitrogens on the other side. Now I'm done. Reaction's balanced. Okay, start with the biggest number and go back and forth throughout the reaction. Okay, how many people have done the third one? Do we need more time or are we stuck? More time? Okay. Okay, so that's what we do for that combustion reaction. Okay, I'll give you a few more minutes on the 4th one there. Okay, and I'll put the 5th one up just in case you're done the 4th one. Okay, just work on those 2 for now, and then we'll go over them in a few more minutes. Let's have a look at the next one here. All right, so in the next one, we've got a single compound as our reactant. What's the only reaction type that starts out with only one reactant? Decomposition. Okay, so this is definitely a decomposition reaction because that's very unique, okay, to have only one reactant. The only thing it can do is break down, okay, or separate. All right, so now we know it's decomposition. Right, now we want to write it out in words. So this is a molecular compound, so I've got to follow my molecular naming rules. Trinitrogen disulfide. It's going to break down into, what's this stuff? Nitrogen. Okay, remember, we don't put a prefix on it because it's an element. Okay, and what's this stuff? Sulfur. And that's like the most special of the special elements. Okay, but it doesn't change its name. That's just the way sulfur appears as an element, S8. All right, so now I've got it written out in words. Now I need to balance it. What should I start with? Yeah, start with sulfur. It's the biggest number. Okay, so 8. I got to go over here and make sure I've got 8 sulfurs. Well, what times 2 will give me 8? 4. Okay, so I put a 4 here. When I put that 4 there, though, it gives me 12 nitrogens. What do I need to put in front of this nitrogen to get 12? A 6. All right, now it's balanced. How many people have done the next one? Okay. Right. I'll give you a couple more minutes to catch up to me. I'm going to take this off of here. Okay? If you're done those, then you can keep going. let's have a look at the next one. All right, so we've got chlorine, okay, as a element. Okay, so we'll write other names here. Chlorine is an element reacting with an ionic compound, sodium iodide. Wow. It falls behind you. Sodium iodide. Wow, that's weird. It's so slow. Okay, is going to produce iodine as an element and sodium chloride as an ionic compound. Okay, what kind of reaction is that? Single replacement. I've got an element reacting with an ionic compound, producing a new element and a new ionic compound. So that fits the pattern for single replacement. Okay, so now I've got to balance this thing. Okay, I got to start with my biggest number. Okay, that could mean iodine or chlorine. It doesn't matter which one I pick here. Okay, so I've got 2 chlorine atoms over here, but I've only got 1 over on the product side, which means I need to put a 2 in front of sodium chloride. By doing that, it not only gives me 2 chlorines, but also 2 sodiums. So I've got to go back over to the reactant side and make sure that I have 2 sodium atoms. Okay, when I put that 2 there, it gives me 2 iodines. That works out because there's 2 iodines over here in the products, and now that reaction is balanced. Questions on that one? All right, how many people have done the next one? Whoa. Okay, let's go through the next one, and then you guys can do the last one after that. Okay, so we've got an ionic compound here, calcium chloride. Okay, it's reacting with another ionic compound, sodium carbonate. Okay, and that's going to produce calcium carbonate, another ionic compound, and sodium chloride. Okay, what kind of reaction am I looking at? Double replacement. Everything in this reaction is an ionic compound. The only reaction type we know of for that is double replacement. Okay. Now I've got to balance it. What should I start with?
The biggest one.
Biggest one. Okay, biggest one is sodium. Okay, a lot of people will make the mistake of assuming that carbonate is the biggest one, but remember, that 3 is part of the carbonate ion. There's actually only 1 carbonate on each side right now. Okay, so we'll start with sodium. There's 2 sodium here, and there's only 1 over here on the product side, so I'm going to put a 2 in front of it. Putting that 2 there gives me 2 chlorine atoms, so I'm going to go back over here. All right, there's 2 chlorines, so that works out. Next in line, calcium. There's 1 calcium here. There's 1 calcium in the products, so that's good. 1 carbonate in the products, 1 carbonate here. It looks like everything is balanced, and all I had to do is add 1 number. And that happens sometimes. Okay, give you a couple minutes to do the last one, and then we'll go over it. Let's look at our last one here. So, in our last one, we've got an ionic compound, hydrogen chloride. Okay, it's reacting with another ionic compound, potassium hydroxide. Okay, that's going to form HOH, which I can write more commonly by its common name. Water. You could write hydrogen hydroxide if you wanted to, but that's 2 H's and 1 O. Okay, that's water, written as an ionic compound. Okay, and then lastly, I've got another ionic compound, potassium chloride. So this is an acid-base reaction, okay, or a neutralization reaction. But more importantly, it's a reaction type we've gone over containing 2 or all ionic compounds, which is it's still a double replacement reaction. Okay, it still involves ionic compounds where their metals are replacing each other. All right. How easy is this one to balance?
Very easy.
Very easy. Are there any little numbers? That means everything in here is a 1. And that also means everything in here is already balanced. Okay? If there are no little subscript numbers, you have nothing to do. That happens very rarely. Okay? But in this case, there's 1 hydrogen, 1 hydrogen, 1 chlorine, 1 chlorine, 1 potassium, 1 potassium, 1 hydroxide, 1 hydroxide, everything's a 1. Okay? Everything's already balanced in that particular reaction. All right, so is it pretty important to be able to write formulas and names? Okay, so if you're still struggling with that, probably come in and see me for some help on that this week. Okay, and you got to practice it. And you've got tons of practice sheets on naming and writing formulas in your workbook package, and you have the keys because I posted them on Google Classroom a long time back, but they're in there. Okay, so make sure you know how to do that and you're doing them well. Okay, and then obviously you need to also go over your reaction types. It's really important to be able to identify a reaction as either single replacement or synthesis or whatever. Okay, that's an important skill as well. All right, so coming up here, guys, as we're going forward, we're gonna have a quiz tomorrow. Okay, and that quiz will have some properties of compounds stuff. Okay, so like what was in our lab, and it'll have some solubility stuff. And I may even throw in a reaction to identify the type. Okay, you'll know from your practice quiz whether I'm doing that or not. Okay, but basically just there's only 5 types, so it's not too much to know. Okay, so you'll have that tomorrow, and then tomorrow we're going to continue working on reactions. Okay, going over some more examples and such. Wednesday and Thursday we're going to be working on your research project for this unit. Okay, so we have 2 class periods to do that, Wednesday and Thursday. Friday, in our short class, we're going to do the pre-lab activities, for our reactions lab, which we're going to perform a week from today. Okay, so we'll be back in the lab a week from today. Reminder, speaking of labs, okay, that your properties and compounds lab is due this week. I just can't remember which day off the top of my head. Wednesday. Okay, so make sure you've got that done. If you're wanting some feedback, okay, on that or some help with that, again, come and see me at lunch, okay, and I'll be happy to kind of go through it with you, okay. But you can take advantage of that as well. Either, well, probably be today because tomorrow I've got supervision all through lunch hour, but okay, you might be able to catch up with me real quick at some point during the day. Okay, so that's coming up due as well. Okay, don't leave it till the last minute. Okay. All right. Also, guys, probably going to be deciding on when your unit exam will be pretty soon. I would say at this point it's likely to be about 2.5 or 3 weeks. Okay, probably less, probably 2.5. Okay, but I'll get a date up there in the next couple of days, so you got lots of notice. All right, if I can get everybody to mask up, clear off their desk, I will come around with the spray.